So let's quickly have a look at what's unique about stationary points and inflection points. So let us have an example here. Y equals to x squared, x minus 6. Let's draw it and understand how it looks visually to what it means when talking about differentiation. Differentiation is so important and it appears in so many different areas. It is applied when talking about a rate. Because it's a gradient, it's a rate of change. So anywhere you see stuff to do with rates in physics, in chemistry, in biology, in engineering, this is really important. It's just the function that differs. Right? So let us have a look at this simple polynomial. We know how to differentiate it now. So we will draw it first and then we will deal with the differentiation after. So we have dealt with how to draw any type of curve, how to draw polynomials quickly before. So I can either expand this into x cubed minus 6x squared and try to draw it from that, or I can draw it from this. And I find it simple to draw it from this this format. But you can see here from the expansion that there is no constant term, or at least the constant term is 0. So what this tells me is that the y-intercept is 0. That's what I can know quickly from that. So how would I draw this? Well, first I will draw something that I do know quickly, which is y equals to x squared, which is that. And then next, I will draw x minus 6, so which is a straight line that has an intercept of minus 6, which is here. So this straight line here. And it has a positive gradient because the number in front of the x is a positive number, it's positive 1. And because the gradient is 1, if this is minus 6, this is 6, right? Perfect. So how can we draw the resultant graph? What's the multiplication of both of this? Well, main parts that I have to look at are here. Let me just use a different color for this. This is an important part to consider, and this is also an important part to consider. So when you look at points beyond 6, well, at this part of the graph, x minus 6 is a positive increasing one, and x squared is somewhere up here. It's also positive and increasing. So my resultant graph beyond 6, in fact at 6, this graph here is 0, so whatever number is multiplied is 0 is 0. And it is increasing very quickly because it's a mixture of x squared and x minus 6 beyond 6. And then another point that is important is here, because x squared is 0 here. So 0 multiplied by minus 6 is 0. So it crosses here. Again, we knew that that's the intercept anyway. And then beyond minus 6 to the left side, to the negative side, you can see that x minus 6 is negative. All these are all negative values of y. But beyond this point, beyond the origin, x squared is positive. These are positive values of y. And positive multiplied by negative is negative. But the number, the magnitude, is still quite big the further you get away from x as you're approaching infinity. So this will do something like drop like this. Okay, so what is happening between 0 and 6? Well, between 0 and 6, x squared is positive values of y. X minus 6 is negative values of y. So this graph is going to be negative. And then it has to get from, you see, we've gone from 0 to 0, but we have an increasing function with regards to x minus 6. The gradient is positive this way. It's going up, okay? And we also have an increasing function with regards to x squared because the gradient is positive that way, right? So what will happen? Any clues as to what will happen here? Please, you can stop the video and write down in the comments what you think will happen at this point. But because we have negative values, this will go down that way, it will reach a peak and then come back up again. If you don't know how to multiply gradients, you could just think to yourself, well, okay, I've got 0 here. 0 multiplying it by -6, but this is increasing, and it is increasing quickly, isn't it? So when I get to something like, I don't know, whatever the number is here, this number here has come down, right? As I am going up, this number here is coming down because it is decreasing in magnitude, isn't it? So I'm going to reach a peak, right? I'm going to reach a peak where these numbers here are going up, these numbers here are going down. It will reach a peak and then come back down again. And this is how you draw that function. So let us look at the derivatives. dy by dx equals to, here is 3, drop down the power, drop down the power minus the power by 1, minus 6 times 2x to the power of 1, which is 3x squared minus 12x. Now, we know this is 0.0 here. What else do we know? Well, so we know that dy by dx at the point where x is 0 is just 0. Well, we could have said that initially, because we know that we can see if I put a tangent here, the gradient of the tangent will be 0. So we knew that, right? But what about at 6? What's the gradient at 6? Well, dy by dx at x equals to 6 is 3 to the power of 6 squared minus 12 to the power of minus 12 times 6. So that's 3 lots of 36 minus 12 lots of 6. So that's minus 72 here. So it's the 36. So the gradient here is 0. The gradient here is 36. But what do we see from this curve? We see that there's another point here that looks like as if it has a gradient of 0. What point is this? What's the value of x here? Well, we know that dy by dx, right? So I'm solving for that point. So we know that dy by dx is 3x squared minus 12x, which I can factorize as 3x, x minus 4, right? And this tells me that when x equals to 0 and x equals to 4, dy by dx is 0. So what we've done here is we found that this is x equals to 4. Now, these are stationary points, right? The stationary points are 0, 0. Stationary points is where dy by dx equals 0. And in this situation, it is where x is 0 and x is 4. This is essentially this exercise that we've done here. Now, the first part of this exercise allowed us to find the gradient anywhere. So we found what the gradient was at 0.6, even though it was not 0. And in fact, you can put any value of x to try and find the gradient at that point, which is very useful. But also, by solving for dy by dx equals to 0, as we have done here, we were able to see all the values of x's where the gradient is 0, where the tangent would have be 0. So that's the origin and when x equals to 4. Great. So what about the nature of the stationary points? I mean, we can see that at the origin, it comes up, then it comes down, and at 4 is a minimum. So there's maximum and minimums when talking about gradient, stationary points. So clearly we know that this is a maximum. It looks like a maximum because it started from a positive gradient, ends up in a negative gradient, and this gradient is 0 here. Okay, these here I'm talking about gradients. M is 0, M is positive, M is negative. Okay, equally for a minimum, we start with a negative gradient. A negative gradient is just dropping, it goes down, or the line is shaped like this. Okay, and this here is a positive gradient, and we passed by a zero gradient. We passed by a zero gradient, and that's a maximum, and that's a minimum. Okay, so when you're doing stationary points and we found that x equals 0 is a stationary point, x equals to 4 is also a stationary point, how do we know without plotting the curve if it's a maximum or if it's a minimum? So one way to do this is by differentiating the first derivative. Let us go through some notation here. Now we know that dy by dx equals to f of x. But if you differentiate again, f dash, if you differentiate again, this becomes d squared y over dx squared. Remember, this is not equal to dy by dx, all of it squared. I've not just done a square here. What I've done is a d over dx of the dy by dx that I had initially. So I have to differentiate first, get the function, and then differentiate again and get the resultant function. And this is written as double dash x. So just going through some notation here. So let us differentiate again. So initially, in my function that I had here, I had 3x squared minus 12x. So dy by dx was 3x squared minus 12x. Okay, so if I do d by dx of this dy by dx, essentially it means I am doing differentiate with respect to x, 3x squared minus 12x. So this becomes just differentiating this part and this part separately as you would, and this becomes 6x minus 12. This is f double dash x. Okay, then f double dash x at point 0, which is the origin, that was our first stationary point that in the curve looked like a maximum, right? Let's check if it is a maximum. F double dash 0 equals to 6, 0 minus 12. So the answer is minus 12. And f double dash at point 4 is 6, 4 minus 12, which is 24 minus 12, and that's 12, positive. Now, what you need to remember here, and you can prove this, and please let me know in the video, in the comments, if you want me to show proof of this, that d squared y over dx squared, when the value here is less than 0, i.e. it is negative, then this is a maximum stationary point. And when d squared y over dx squared is greater than 0, this is a minimum stationary point. And our example above just shows that that's the case. We have been able to use the curve, the plot that we have just drawn, and we have shown that it is true, that this generalization is true for the curve that we have drawn. So where does this talk of inflection points come from? Like, what are they? So this should just take a few minutes, but it is really important. So an inflection point is where the tangent to a curve crosses the curve. So let us talk about another example here. So inflection points. Let's have a look at this curve here. This is y equals to x cubed, right? So dy by dx of this is 3x squared. And d squared y over dx squared, so I differentiate again, is 6x. But what is peculiar about this? Does it have any stationary points? Does it have any maximum and minimums, etc., etc.? Well, if you look at the curve, I don't see any maximum and minimums. However, dy by dx at the point where x is 0 is 0, right? So based on our talk of stationary point, that should be either a maximum or a minimum. But does it look like a maximum or a minimum in the curve? No, it does not. So what's the nature of this point? Well, if you look at d squared y over dx squared, this at the point where x equals to 0, this is 6 times 0, it is also 0. So it's neither positive or negative. So you can see here what is happening. We are starting with a gradient that is positive, and then it continues this way. It kind of like slows down and in fact ends up with a tangent where at the point of origin here, the gradient is 0. So it's like almost, well, it is actually flat at the origin, and then it picks up again. It's positive again. So it's not going to positive, it's not going from positive to negative, negative to positive. It's going positive to positive or negative to negative. But it is 0 midway. So, and this is what an inflection point is. The tangent is crossing the curve itself. Let us look at another example that's similar to this. It's also a polynomial, whereby y equals to x to the power 4, right? Well, dy by dx is 4x cubed. D squared y over dx squared is 12x squared. Again, similar situation. Dy by dx is 0. D squared y over dx squared, also known as the second derivative, is also 0. But here it's a minimum. What's going on? So to be able to know if something is an inflection point or a maximum or a minimum, the sure way is to just check what is the gradient before and what is the gradient after. So just pick a point beside the origin. Like for example here, I would pick a point 1 and I would pick a point -1 to check the gradient either side of the point of interest to see if it's a maximum or a minimum. Because here you will find that the gradient either side is positive, but the gradient here will be negative because it's this is dropping, and the gradient here will be positive. So that will tell you it's a minimum or a maximum or neither of those, right? So yeah, and that's the end of the video. Don't forget to comment if you have got any questions. If you have any questions regarding other videos you want me to do, please do comment them, and don't forget to subscribe.